Yeah. Okay.
Hey there, John. Good to see your smiling face. I'll bring our team on for introductions here momentarily. I see a few more folks ticking in, so I'd like them to be able to join the start. Hey there, Mitch. So let me make sure that I've got my Q&A dialog open, chat box, all the little widgets. I need 5 screens for a webinar like this. Can you guys hear me okay? I heard a note from Janice that she can hear us, so hopefully, and I'm hearing you guys, so I think we're looking good. All right, looks like we're a couple of minutes in, and I see it looks like our participant number is stabilized. So why don't I begin? Thank you all for joining us on a Thursday morning, Eastern Time. I'm Carl Bangert, General Manager of Flex Structures North America. Thank you for attending this webinar on Industry 4.0, process validation and product validation and process virtualization. We'd like to talk about some of the ways in which data that you already have in your CAD and CAE systems can be further leveraged to do visualization validation of flexible systems, including design layout, as well as taking into account considerations for manufacturing and assembly on the computer as well as in VR. That is our agenda for today. As we move forward, we'll first introduce Sandalwood and Flex Structures. So you know the smiling faces you see here, and then we'll turn it over to the computer. A lot of the work that we've been doing jointly has been in the area of Industry 4.0, whether it's the Internet of Things integration, cybersecurity, working with model-based design in the engineering segment. And as we're talking, our agenda today is on product validation, process virtualization. That's going to, we're going to move from one area to another, beginning with some work that's been ongoing for a number of years now in cable simulation and hose design, essentially modeling flexibles, path planning as it relates to looking for viable assembly operations, ergonomic considerations, and then moving into a VR environment. Questions are open anytime. We'll be monitoring the Q&A and chat boxes. We'd like to make this an interactive session. So I'm from Flex Structures. We're here with our technical partners from Sandalwood Engineering and Ergonomics. I'll turn the microphone over to John Lukowitz, who will introduce his team and say a few words about Sandalwood.
Good morning, everyone. My name is John Lukowitz. I'm the technical lead for digital engineering with Sandalwood Engineering and Ergonomics. So Sandalwood, we're an engineering consulting and services firm. We were really born out of Ford's advanced manufacturing technology division, but we do work with a variety of clients in a variety of industries, you know, both inside and outside of the automotive industry. We were founded in 1989, so we've been around for quite a while now. We have offices all over North America. So in the US, those would be in Detroit, Michigan, as well as Louisville, Kentucky, in Canada, in Toronto, and in Mexico City, in Mexico. And our organization is really made up of 3 divisions, 3 lines of business. And those are injury prevention, which is primarily focused on things like safety and ergonomics. systems engineering, which is my team, working on things like project management, manufacturing, and also supporting our clients with a variety of advanced manufacturing and digital engineering tools, some of which we'll see today. And then systems integration, which is primarily focused on controls engineering. And at the end of the day, what do? We utilize advanced technologies to assess and manage risk for our clients, employees, processes, and systems. And we're very excited to be here with you today.
I'll turn it to Mitch to say a few words about yourself.
Yeah, awesome. Thank you. Good morning, everyone. A little bit about myself. My name is Mitch Carswell. I am one of our team leads on the injury prevention lines of business. I'm a current certified professional ergonomist, something that I worked to achieve last year. I'm also one of our resident subject matter experts on digital human modeling. So I have a lot of experience in that field. So excited to share what the IMA mannequin is capable of doing in today's presentation.
And a quick shout out, Mitch will, in the last week of March here, Mitch will be presenting at the Applied Ergonomics Conference in New Orleans about some of the work that we've been doing, utilizing IPS tools to further ergonomic investigations. So hope to see our ergonomist friends there. We also have Johanna Kroos here as well to say a few words about herself and her roles.
Hi, everybody. My name is Joanna Kroos. I'm also a Sandalwoodian. I work on the SE team with John. My work primarily right now is project management work and process engineering. And I recently took on a role supporting the Institute of Industrial and Systems Engineers, leading our initiative to revive IISE as the president. So I'm part of the interim leadership team with Richard Alowoyan, who's the vice president, and Dana Hammond, who is our current treasurer. So the Institute took a pretty big hit with COVID and died out. So we are stepping in and trying to revive the organization and provide value to the memberships. So our main focus right now is trying to spread education and being a really good resource to our members to learn more and see insight into other industries and make good connections with other people. So we're trying to grow the community. So if you're not already a part of IISE, it has a lot of really great benefits. And if you drop your email in the chat, I'll make sure to collect that and reach out to you later about opportunities to get involved, how you can get an IISE membership, what the more detail on what the benefits are, or if you just want to have a conversation to learn more, would be happy to do that. So thank you.
Great, thank you, Joanna. Just a side note, the IISE is the sponsor of the Applied Ergonomics Conference that I mentioned a moment ago. So very good to see the activity in the organization returning here post-COVID with a live event in New Orleans, which looks to be well attended, and I'm hoping to make strides in that area as well. So continuing on with ourselves, so I represent Flex Structures North America. The mothership of Flex Structures Germany was founded 11 years ago in Kaiserslautern as a high-tech spin-off of the Fraunhofer Gesellschaft, the Institute for Technical and Business Mathematics. There was initial work that was done in the aughts to look at ways to simulate in real time flexible elements in vehicle systems using newer math, and that is led to the founding of Flex Structures. Flex Structures is now a global presence. We have partners in the Far East, as well as offices and distributors in Europe. And here in the US, as you mentioned, we have partnered with Sandalwood Engineering and Ergonomics to bring the IPS, the Industrial Path Solutions technology to you. The motivation for this really has come out of what we've seen, the developments over the decades, primarily driven out of the automotive industry. Our vehicles are getting increasingly complex, especially as it relates to the miles of cable and wire, the lines of code in our vehicles these days. And an important aspect of managing that, we're seeing that accelerated due to the strategic decisions by the major OEMs worldwide to move towards electric vehicles and electrification. So there are a lot of challenges, as I'm sure the our attendees here know, and managing that complexity is a challenge that been able to support our clients with, and wish to carry that on here in North America as well. One of the, I guess, an example that we presented jointly with BMW, a longtime client of ours, is this move toward virtual prototyping and virtual validation, where in the past, mock-ups of vehicle systems included physical bucks, 3D printed materials, a lot of time and effort put into making a test floor to look at routing configurations. And BMW over the years from about 2015 to 2018 really moved in the direction of virtual validation, where they were able to realize what it is where their wires, cables, sensors are going to be well in advance of SOP, thus reducing the last minute manufacturing hiccups, and also getting a better handle on warranty issues that might cause problems further down the road. In both cases, a savings of both time and money. The new process is a hardware prototyping floor that is basically empty, with much of the work being done on computer systems. So that is really what we're going to describe here in the product portfolio here, and really the solutions toward doing cable simulation virtually, coupling that as we move toward manufacturing with assembly path planning. So how can ECUs, how can harnesses be integrated within underhood spaces, within the dash and what have you, taking human factors. That's why we have our economists here on site as well. Once we've determined a path, is that something that a human and an operator or worker can assemble? What are the considerations, whether it comes toward access, field of view, clip strength, shoulder strength, and so forth, and then making that happen in a VR environment, which helps to bring this sort of development even further ahead in the system to do what if studies way in advance of the work that's being done. So that's an overview of what we'll be talking about here in the next hour or so, and I won't belabor that anymore, and rather turn the mic over to John Lukowitz to show you live what's taking place in IPS cable simulation.
Thanks, Carl. Let me share my screen. Okay, so as Carl mentioned, we will be going through an overview of the entire suite of tools. As we go through these demo models, these exercises, just keep in mind that all of these modules can work together or independently. So you can use cable simulation with or without IMA and VR and vice versa. So basically everything that you'll see today is all under one IPS toolkit, and these tools can be used independently or together. And we will begin with cable simulation. So we've got an example here of a brake line in a corner suspension, and we are going to analyze and optimize this cable, and then see how we can feed some of this information back into our CAD or PLM system. Keep in mind with this cable simulation exercise that although we're looking at, a brake line, a tube, the methodology for designing or optimizing your flexibles in IPS is really the same, regardless of the kind of flexible that we're looking at, right? So whether that's a multi-branch harness, a single wire, a hose, a cable, even a preformed flexible like a coolant tube, the methodology is really the same. So first, we need some CAD data. And in this case, this is just some JT data that we were able to pull in from the CAD system. IPS is compatible with a number of file formats, including JT, OBJ, PVZ, STL, VRML, as well as CATIA formats. And I should mention here as well that we are compatible with a few different point cloud formats, if that is something that is of interest to you as well. We've also seen some of our clients establish direct connections between their PLM systems and IPS. So we've seen direct connections from PTC Windchill and Creo View, as well as from Siemens Teamcenter directly into the IPS tool. So we brought in our CAD data, and now we want to analyze and optimize our break line. We can create flexibles from scratch in the IPS tool, right? If we just know where the cables are running from and to, we have some fixation points, we can route them from scratch. But we can also take pre-existing 3D geometry, make it flexible, add some material properties, do our analysis and optimization, and then feed that information back. So in this case, I've got some pre-existing geometry from the CAD system, and I'll just select it and use a tool called the Cable Finder to automatically find that flexibles geometry. So we can see that the software has very quickly identified the center line for this break line, and we can see a number of cross sections along it, identifying its geometry. Then we just need to tell the software a little bit about the type of cable. So what is its cross-section profile? And then very importantly, what is its nominal shape? So again, we can simulate straight cables, a cable that would be straight, when unloaded. But we also have the capability to simulate preformed cables. So if you have some kind of flexible that's pre-bent into some configuration, like a rigid brake line or a coolant tube, we also have the capability to simulate those kinds of preformed cables as well. And then lastly, I need to tell the software a bit about the materials that make up this cable. So we can define these parameters ourselves, tell it a little bit about its cross-section and radii, if it were a tube. Or we can use an instance from the library of hoses and cables that comes with the IPS software. So in this case, I'll just select the brake hose, 7mm brake hose, and we can see those material properties and cross sections pop into the dialog here. And I will just click OK and create cable. And now we have successfully made our just dumb 3D geometry from the CAD system flexible in IPS. And now we can see that if I were to move the ends of the cable, we can see it behaving, very realistically according to its specific material properties. This is sort of interesting because this cable is very torsionally stiff. If I were to twist the end, you can see that it immediately goes into bending. And you can see how quickly these flexibles react in the software. So the software is very, very interactive. So now that I've created my cable, I want to take a look at how it's going to behave in this corner suspension assembly. So I already have a motion here that I can just attach my cable to. But we can create motions in IPS directly just from scratch by defining a series of points that we want some geometry to move between. But important to note here that we can also import in motions from a CAD system. So we, in many cases, we even see we have a very complex kinematic mechanism with a series of interdependent links. And we can get that data out of the CAD system, bring it into IPS so that, you don't have to recreate these motions and redo all of that work. So now I'm just going to connect my cable to this geometry. Like most things in IPS, it's just a simple drag and drop. And then I'm also going to unwind my cable just to make sure that I start with a torsion-free routing, a torsion-free solution here. And now if I play through my motion again, we can see the behavior of this flexible. We can see that it looks like it's fairly significantly overstretched. The cable looks like it's really not long enough for this application. Now, beyond being able to just sort of observe these things and play around with our routings and our flexibles, we also have a number of very powerful analysis tools built into the IPS suite. So for instance, I could create a color map on this cable. We can create visualizations of a number of different things, right? So we could look at stripes for curvature, a number of different forces, moments, stresses. But in this case, I'm going to take a look at the bending radius. And then I can customize this map based on my design requirements. So let's say in this application, bending radius of 100 is ideal, and our minimum bending radius is 25 millimeters. I can customize that map. And if I play through my motion again, we can see this visualization updating in real time, indicating that we have a problem with this design, right? We're dipping below that minimum bend radius value. We can also directly measure any of these values, right? So beyond just visualizing them, we can create value measures on our cables to measure any number of different things, right? So we can look at things like elongation, tension strain, any number of different forces, moment stresses, contact force. I'll just create another value measure here for the bending radius. And we'll see any of these values that we're tracking pop up in the bottom right-hand corner of the screen and be tracked in real time. So we can see how these values are changing over the course of our motion. So we can see here that our bending radius is dropping, very low. I think it's going as low as about 4 millimeters here. And, to alleviate this condition, we could play around with the routing of the cable, where the fixation points are, where these fittings are located. We could also very quickly change the length of the cable. So if I just right click on my cable here, I can increase or decrease the length, either just with these up or down arrows or the slider, or I can just type in some value here. And then we can replay our motion to see how these changes have affected the values that we're interested in. Beyond just, sort of manually looking at these values that we're interested in, we also have some really powerful analysis tools. So I can create plots or maps of or graphs of any of these values that I'm interested in. So if I take a look at this graph for the bending radius, we can see how those values are changing over time. And let me just change this color. It's a little dark. There we go. So we can see directly how this bending radius value is changing, over the course of this motion, over the operation of the vehicle. And we can do some interesting things like drag through and see how these values are changing. We can also define upper or lower thresholds. So for instance, my minimum required bending radius here is 25 millimeters. So I could identify all of the areas on the graph where we're below that value and take a look at the flexibles behavior in those areas. I can also search for either global or local maxima and minima, or even specific values. So in this case, I'll take a look at my global minimum bending radius. And if I hit find, we can see that the software has identified for us on this graph exactly where that minimum bend radius is occurring and its value. So it looks like our minimum bend radius is still about 7 millimeters, well below our minimum required value. And if I hit go to, I can jump directly to that point and take a look at the behavior of the cable in this worst case scenario. So again, in this worst case, I can try to change my routing or the length to optimize this routing and make sure that we're staying above that minimum. So I'm just going to right click here and change my length again to try to get above 25. We can see that value tracked in the bottom right-hand corner of the screen. And it looks like at a nominal length of 220 millimeters, we are above that 25 millimeter minimum. And again, I could drag through and see the behavior of this cable over time. If I like the changes that I've made, I can just click this green check mark here to save those to the scene. And we can see that we have a significantly improved routing here just by increasing the length of this brake line. Some other interesting things we can do, now that we've increased the length of this cable, That can also cause some other concerns, right? So a longer cable may have worse clearances to surrounding components. For instance, it looks like we're coming a little closer to this piece of guarding here. So I can create distance measures as well in IPS to directly measure the minimum distance value between components. It's very easy to do. I just need to tell the software what I want it to measure from, in this case, my cable, and what I want it to measure to, this piece of geometry. And we can see a line here identifying where that minimum clearance is occurring and what that minimum distance value is. And again, all of these values are tracked in real time. So we can see how that distance is changing over the course of the motion. I could also analyze this distance measure. So I'll just rerun the analysis here for my distance measure and my bending radius. And now we have two plots showing how both of those values are changing over time. So we'll just double check here. Again, I'll find my minimum bending radius. Looks like it's a value of, oh, my values didn't change. 1 second. Back to the longer length, rerun my analysis. So now if I find my minimum bending radius, we can see that that value is about 26. So it's above our minimum required value. And then I could also find my minimum clearance value here and jump to that position. Looks like our minimum clearance is about 28 millimeters. So if this design is acceptable, then we have successfully optimized our brake line in IPS. And now we would want to feed this information back to our CAD or PLM systems so that other engineers, other designers are aware of the changes we've made. And that's very easy to do with the IPS tool, and there are a number of ways to do so. So first of all, I can export the center line of this cable in some static position in a number of different file formats. I could also export out just the 3D geometry of the cable in some particular configuration in those same formats. We can also create motion envelopes. So if I want to capture all of the design space that this cable is going to move through, to inform other folks to not put any components in that area, I can just select my motion and create a motion volume. And then I just need to tell the software what I want it to capture as part of this volume. So I'm going to turn off everything except for just my cable. And let me just check my settings here really quickly. And I can generate a swept volume of all of the design space that this flexible is going to pass through. Another thing to note here is we can also create these motion envelopes relative to other components, which can be very interesting for certain applications. So here we can see my motion volume, and I will just change the color and the transparency. And if I replay through my motion, we will see that the cable is not passing outside of this envelope that the software has determined for us. So again, this is something just like the 3D geometry of the cable or the center line, we can very easily just export this information out to share it with others. One more thing I would like to share with the, sort of the outputs. We've been looking at this flexible thus far almost completely, with nominally, right? So we have a nominal length, nominal material properties, nominal position and orientation of the fixation points, but we can also use the IPS tool to look at it with some tolerancing. So I can create tolerance envelopes for the cable as well, and allow anything about it to vary, right? So its length, its material properties, the position or orientation of the fixation points, and I can do this with or without a motion. So just as a quick example, I'll allow the length of this cable to vary plus or minus 10 millimeters. And I'll run this without the motion, just in this static position. If I hit generate, we can see that this generates a swept volume of all of the area this cable could take up if its length were allowed to vary plus or minus 10 millimeters. So some very interesting tolerancing tools built in as well. And that concludes the cable simulation portion of the demonstration. Carl, do we have any questions?
Thank you, John. I'm looking for questions coming in, and one that's been brought up is, could you explain a bit on how you determine cable and hose properties and how they're entered into IPS cable?
Yeah, absolutely. So let me edit this cable so we can see our properties here. So there are several ways to do this in IPS. We can use basic parameters, just density, Young's modulus, Poisson ratio, and this assumes a homogeneous material throughout the flexible. We can also use our library that comes with the IPS tool. Oftentimes these basic parameters can be they're good enough for many studies. If you want to look at the shape of your cable, kind of how it's behaving, where it's moving. But for really critical applications, we can also use these effective material properties. And these are determined by direct physical testing of our cables. And through our partners in Germany, we offer testing services with something called the Mesomics machine, which is a piece of test equipment that will determine these exact material properties for you. And then you can directly input them into the software to make exact behavior of your cables and hoses.
Very good. Thanks, John. Are you there?
Yeah.
Oh, okay. Another question that's been brought into our chat is regarding the tolerance envelopes or tolerance analysis you were doing. Can you show the envelope if we had plus minus tolerance to, let's say, the length? Could you touch on that?
Sure. Yeah. So as I showed here, if I select my cable and pull up the tolerance envelope, again, we can allow anything about the cable to vary, right? So that could be the length, material properties. So as an example, just plus or minus 10 millimeters for the length, we can generate that swept volume. Another thing that's interesting with these tolerance envelopes is, let me pull this back up. We can also allow the fixation to vary, right? So I could allow, let's say, the orientation of this fitting to vary about the z-axis, right? Which in this case would be along the length of the cable. And we can see, if I give this, I'll give it quite a wide value, plus or minus 20 degrees. Oh, 1 sec. Gotta add in my cable. Why is it mad at me? 1 sec here. There we go. You can see how that orientation change at the fixation point is going to affect the shape of the cable, which in this case it looks like is not very much. And again, we can do this with or without the motion, right? So we could also include a motion in here and generate a much larger value, which with much more variance.
Thanks, John. So that essentially introducing a twist at that point on the assembly.
Correct. Yes.
We have another question from our attendees. Wire harnesses have many different coverings: spot tape, protective tape, sleeves. How are you accounting for that?
Yeah, that's a great question. So in the IPS tool, what we're trying to do is look, at a high level at what's the behavior, the physical behavior of these flexibles. So based on your material properties, those would take into account the various coverings. So, we're not really taking a look at, microscopically what's happening with each strand in some particular cable or bundle. We're taking a sort of a higher level look at the overall behavior of the bundle. So we could approximate that behavior with some basic parameters, right? Or if we needed a really critical in-depth study, we could use these effective parameters, have that particular cable or bundle or flexible tested, and that would take into account the stiffness that is added by the covering.
Right. And then there's also the perhaps a quick view on the bundle stiffness estimator, which I believe is also in the process of getting enhanced for our June release.
Yes, yeah. So this the cable stiffness calculator is another way that we could approximate the stiffness of some particular bundle, right? So if we tell the software the number of wires, the diameter, the insulation, some information about the insulation and pitch length, we can use these values to approximate the stiffness of a particular flexible.
Right, and we did have another question. Can it calculate the flexibility based on the contents, like type of wires and covering? And again, the best case for that is to do testing in the Masonics machine that was developed specifically for IPS cable simulation, but there's also the approximation then that can be done using the bundle estimator.
Absolutely.
And and then there are also situations, I believe, that you've modeled where, especially for hoses, there are stiffener coverings that provide different properties as well, right, John?
Yeah, absolutely. And we can model those with basically telling the software that it's actually a series of different cables that are connected together, right? So if we had a covering, along the first 100 millimeters of this brake line, we would simulate that as a separate cable connected into this main one, so that we could give that first 100 millimeters, some different stiffness values to account for that.
Great, thank you, John. So we've had some good interaction there. I think at this point, let's move on to the path planner.
Great. Let me share my screen, my other screen. Okay. So moving on to our next tool in the IPS toolkit or IPS suite, we're going to take a look at the rigid body path planner. So the rigid body path planner is a tool that allows you to plan a collision-free installation path for any object between, just a start point and an end point. And this can be useful for a number of different kinds of applications. In this case, we're going to take a look at an application with a piece of tooling. So this is a lift assist that needs to pull, this is an engine damper from this tray, and it has to have a fairly complex motion to be able to kind of twist and hook into one of these spokes on the damper. So we're looking in this case at a tooling application, but just keep in mind that this can be used for any object with some obstacles and a start and an end point. So we often see our clients use the path planner tool for installing some component into an assembly to prove that it's feasible and look at what those clearances are. We've even seen some clients use this for planning equipment installation, right? So there's a number of different constraints we can put on the algorithm that plans the path. So we've seen folks say, I've got to get a piece of equipment in through this bay door and through my plant into this final position. And if you have CAD geometry or a scan of that area, we could plan a path and take a look at those clearances. So just any object with a start and an end, and you can find a collision-free solution. So in this case, all I need to do, it's very simple to use, is select the object I want to plan a path for, in this case, my hook, up the rigid body path planner tool. And then I just need to set a start point and an end point for this path. So this will be my start. And then I'll jump this hook into the end position, set that as my goal, and then give it some space to try to find a solution in. So we can see the box here that the software will try to find a collision-free path in. And then basically just tell it to plan. And the software, is going to work out if there is a way to get from point A to point B. The calculation time depends on, the complexity, how tight the clearances are, how many obstacles there are. But in this case, this is really quite a complex installation, and the software was able to find this path in about 7 seconds. So it does work very well. If I open up my motion player here, and I'll just slow down the path a bit, we can see that this initial path, it's very choppy, right? So it's sort of unrealistic in terms of how an operator would perform this sort of task. But we can very easily smooth this path. So, right, so this is just the initial solution that the software found. So I'll just smooth this path 20 times to try to get a more realistic simulation. And now you can see how this white line that's identifying our path has changed. It's much smoother now. And now if I click play, we'll see this much smoother, more realistic installation path for our damper hook. If I'm happy with the path here, I can just hit save to scene, and that will save this installation path into my simulation so that I can refer back to it and play through it. And then, similar to the analysis we saw with cable simulation, I can use that same tool set, those same analysis tools for this path planning. So for instance, I could create a distance measure between my hook and, let's say, my damper as well as the trays. And again, we'll see that line pop up indicating where that minimum clearance is occurring, and that distance measure shows up in the bottom right-hand corner of my screen. So now if I click play, we can see how these values are changing over time. And I can do the same analysis, right, where I can pull up a graph that shows that clearance. Change the color here so it's a little more clear. Over time, drag through, identify minimum clearance, what the minimum clearance condition is, and really, in many cases, if we're looking at a component installation that's going to be done manually, we want to make sure that there is sufficient clearance for an operator to actually, perform the task. So pretty powerful analysis tools built in here as well. One more thing I'd like to show with the path planner, well, really just the entire suite, right? Because this can be used for anything. We can also create collision tests. So if I want to create a collision test here, I can just tell the software what to check for a collision from and to. So in this case, again, I'll do my hook versus everything in the scene. And now if I just move my hook into a position where it is colliding, we'll see that it's turning red, and the software is indicating in the bottom right-hand corner of the screen that we are in collision. This can be really helpful for identifying, where and when collisions are occurring. But what's a little more interesting probably is some of the other collision modes that we can take a look at. So right now I have it set to just highlight where the collision is occurring. But we can also take a look at intersecting lines. So to capture all of the intersecting lines between our two colliding geometries, or we could take a look at colliding triangles, right? Capturing all of the triangles in the tessellation of these two geometries where they're actually coming into contact with one another. So if I just select intersecting lines here, I can move my hook back into position. And then let me just change the transparency here a bit on my tray, so we can see that a little more clearly. And you can see how it's identifying everywhere that collision is occurring. And then we can even capture this geometry. So I just right click and say capture geometry. It captures those lines, so we can export these out and feed them back to some other engineer or designer, so that they could potentially make some design changes based on this information we're getting out of IPS. And that's really it for the path planner. It's really quite easy to use.
Great, thank you, John. You took care of one thing that had come up, which is exporting that calculated geometry, and also can the calculated path be exported to CAD/CAM system?
Yes. So we can unlock. So if I unlock this motion, we can see that, all of the frames within that path. And I believe we should be able to export motion, and we can do that as an XMO XML file. So basically just each of these frames position and orientation versus time. I should mention here as well, again, it's all the same tool set, right? So if it were relevant, we could also create like a motion envelope, a motion volume for this particular installation. So that would be another potential output from doing this kind of path planner. And in this case, it's the swept volume would be quite large, but this could be useful information, in particular for like a component installation. Hey, we have to move through this area of the assembly in order to install this component. Let's make sure we don't put anything else here.
Yeah, that makes sense. Can that also be used? You're using the example here is with a hand tool, but what about for larger engagements, perhaps a vehicle or trolleys on a shop floor?
Yeah, absolutely. I mean, the size of the planning object really is sort of irrelevant. As long as we have a piece of geometry, a start point and end point, and some geometries that we want to avoid on the way, from point A to point B, if there is a way to get there, the software will find it.
Excellent. Thank you, John. Perhaps now, since we've got this model up, we could, you'd mentioned the human factors aspect of this. Perhaps we can turn this over to Mitch now to look at the ergonomic factors.
Yeah, absolutely. Thanks, Carl.
Yeah, for sure. I'm just going to steal the ball here from John, and I'll share my screen. And we can see that we have a very similar environment to what John was showcasing here with our lift assist end effector, but this time we do have a human model brought into the scene. So our human model is known as the IMA mannequin, or the intelligent moving mannequin, and it's made up of, I believe, close to 84 separate segments that could all be manipulated individually, which allows for a good amount of fidelity when we're trying to get an assessment going here. We're able to create mannequins in either what's called a mannequin family, which is going to be a series of mannequins that all act as one. And this could be as little as 2 mannequins up to 10 or even more than that to assess different anthropometries and different body shapes and sizes. We could also create singular mannequins, so using our anthropometric databases that are available here, or we can utilize custom values if we know a body weight or a stature, and we're able to use these to create our mannequins. So with regards to our IMA mannequin that we're showing here, we can manipulate this in a bunch of different ways. We can just move where it's located on the scene by moving it around. And we can also choose just to move individual components of the mannequin by opening up the placement editor on there. And we can move individual components of the body around. So we're seeing that as I'm moving my mannequin around, or just the hand, the mannequin is following that hand and attempting to posture based on the goal. And what we can do is we could utilize constraints to prevent this mannequin from moving. So our mannequin is tied directly to what's called our floor. And the floor is this little area back here. And this will allow us to set an X and a Y translation area. So if I go to our constraints, we can see that this mannequin is permitted to move infinitely on the X and Y axis. So basically along this floor, and it's restricted in the zones. So it's not going to be able to move in any particular height. So I can move our floor over to here. And then once I have that floor again, I can add constraints to that floor. And now when I move my mannequin, it should stay in position. But what we want to focus on here is how we can utilize the mannequin in conjunction to what John was looking at. So we have our original design for that lift assist end effector, which was actually a straight design that would go into this damper and be controlled by the mannequin. And we can actually look at that motion there. So if I open our motion player, we can take a look at that original motion. So from that perspective, it does look like we have a clear motion. I'm going to slow that down as well. And we can actually play that back and see that this is actually getting pretty close to this dunnage. There is enough room. However, if we did have a hand placed on that lift assist, there may be issues with hand clearance. So utilizing what's called grip points within IPS, we can turn that on. We can have the mannequin or the hand attached to the end effector. And if I bring this onto my mannequin here, he will assume the posture and that grip. And when I play through that motion again, this mannequin will actually follow that path. And using the software, it will attempt to hold on to that lift assist to the best of its capabilities and move through the motion. So we can see that at a few points in this simulation that we're showing, there are some issues with the clearance. And I'm just going to play through and pause on one of them. We can also see that the mannequin is attempting to move. And if I pause like right here, I can turn this off. And we could see that the mannequin is actually losing the ability to hold on to the handle based on the restrictions of the range of motion. And these are going to be applied from standards that exist within the field of ergonomics. So based on the limitations of the joint, we could see that we may have some concerns with this particular lift assist design and running into our object here. So using this information, we were able to go back to the supplier of this particular lift assist, and we were able to actually modify the design to what John was showing. I'm just going to reset my motion. Motion player, there we go. Reset my motion. And we can see that on this updated design of the lift assist, we now have a 30-degree bend in that hook. And so without too much hassle, I can change my grip point or what's attached to my mannequin from that original lift assist design. And I can bring that over to my current mannequin and they will follow that as well. Something else that John had mentioned previously was the use of collision avoidance. And this is something that we can utilize with the human aspect as well. So by going into my mannequin, I can enable collision avoidance and I could set what my obstacles will be. So in this instance, my obstacle will be this entire tray here. So we can add that tray here. Go. Okay, it's showing up there. And when I okay, now when the mannequin follows the motion of this lift assist, it will try its best to avoid any areas of this dunnage while moving. So I'll just play through the motion of that now to see what effect that has on the operator's ability to grab that dunnage, that damper out of the dunnage. So when I press play here, let's do this. Slow that down for everyone to see a little bit better. But we can watch the mannequin follow the lift assist, maintaining a much better grip on that handle while moving through a variety of motion and bringing that up. As well, we can do throughout this entire motion, we can identify a posture that we wish to evaluate. So let's look at something like here. And we're able to open up a static evaluation. Our static evaluation will allow us to do a postural assessment on the mannequin itself. And utilizing a REBA analysis, we can look at all of the different areas based on the joint angles and come up with a cumulative score to assess the posture. So as I mentioned before, we can also do this with a series of motions. So perhaps we are also going to look at something along the lines of a damper in the rear. This can be quickly completed. So I'm just going to reset my motion here. And I will detach my mannequin from the grip point. And now I will turn off my current mannequin and turn on our mannequin family. So in our mannequin family here, we have two different operators. One is a shorter female and one is a taller male. As we typically would assess for ergonomics, it's not just for one direct population, but as opposed for a range of populations to ensure feasibility. So, and just in the interest of looking at something different, we're going to look at as if we were pulling the dunnage from, or the lift assist from that, the damper out of the rear position of the dunnage. I'm going to ensure that my collision avoidance is turned on for this mannequin family. And then I'm going to make sure that that's all there. My objects are in selected, so they will avoid both of those objects. And now I can also just apply my grip point to my mannequin family as opposed to the individual mannequin. What we can see here is currently there's not a way for the shorter operator to grasp that handle without moving the collision, without going through a point of collision. So I believe if I just take her right hand and move it up slightly, I have to release the grip point. Do that. And now we can apply that grip point again. And now we have our mannequins grasping that same envelope. That lift this is now. So when I play through that motion again, we can see that both mannequins are going to go through the motion, attempt to grasp that part. And we can see that they were successfully able to do that in this particular scenario. I'm just going to review this one more time, and this time I'm going to de-render the male mannequin and observe the shorter female here. So when looking at the shorter female, we notice that the hand is above the shoulder, which could be a potential risk for ergonomics. So we're going to pause that there when they're just starting to engage it, and we can look even before that when their arm is actually higher, elevated higher. And we can perform a postural analysis on that aspect as well. So here, I can go to my mannequin family, and I can open my static evaluation. And now this will complete, because we're using a family here, this will complete that REBA analysis for both the male and the female mannequin. And we could see at the end here, we have our total score for our REBA analysis, showing that our shorter female has a higher REBA score, so has an increased risk when compared to the taller operator. So what we can do with some of this information is we can identify that, you know what, this possibly comes from reaching over shoulder. So what if we looked at raising up our mannequin and possibly adding a platform for them to work at? Well, by altering the location of our mannequin platform, we can raise them up, or the floor for our mannequins. We can raise them up and run through that assessment again. Just forgot to save it. That's on me. Go to there. Close that. And we could see that if I turn on our male mannequin, it will also be adjusted because we're manipulating the family. And if we play through the motion of our updated assessment here, we could see there's a lot less risk of a collision between the mannequin and the dunnage itself. And we can review our static evaluation to see that we have improved our REBA score for this mannequin. Within IPS, you can also do line of sight assessments. So you can also apply a vision cone and have them look at a specific area. So I can create a viewpoint. I will apply that to my family. and you can see that their tendency is now to look at the defined viewpoint. And I believe we can detach them or move that viewpoint if we wanted to, have that go to there. And now we know that they're looking at that damper and where they're going to be attaching it. And we can go along and assess like that. So I think that brings us to the next portion, which is going to be our virtual reality portion. And John, if you're okay, were you able to team viewer in to my computer?
1 sec.
Yeah.
Make sure I'm in there.
While we're doing that, Mitch, does the IMA or does IMA take into account the weight of objects? For instance, if that a damper was weighed significantly more or less, would we see a change in IMA's actions?
Yes. So based on forces that are applied to different objects, it will affect the default posture that the mannequins utilize and how they achieve that posture. So there is a posture prediction that is built into the IMA mannequin, and based on the location of the hand as well as the force applied, it will alter the posture of the mannequin. Currently, there is not a way to assess the force or a max acceptable force with IMA, but I believe that is something that is in discussion.
Great, thank you, Mitch.
Right.
I'm in.
You're in. All right. So we'll hop over to our next scene and we'll start talking through some of the capabilities of IMA with VR and IPS within VR. So John, if you could just minimize this one and hop over to the other scene. I'm going to get my headset warmed up here.
Sure.
And when I'm ready, you can launch me into the VR environment.
All right. And while you're doing that, I guess just a brief explanation of sort of what we're doing here. So IPS VR can be used in a variety of different modes. So you can use it in an individual mode where you're basically just in a headset and you could the view can only be seen in that headset. We can also use it in a dual mode where you can make changes in the PC environment that will then instantaneously basically update in the VR headset environment. So Mitch and I are not in the same room right now, but we're using an application to basically have remote logged into his PC. And then while he's in the VR environment, I can make changes in the scene that he sees update instantaneously. So it's just another way that you can work together in IPS VR. Certainly doesn't require 2 users, right? You can make changes in the VR environment to the scene, move things around. We'll see some of that functionality. You could also, just take the headset off and make changes, but working in this dual mode can be really beneficial because it can allow someone to sort of experience your scene, your manufacturing environment, your product, whatever it is that you're looking at in IPS VR, while another user can very quickly make changes, and you can both sort of assess the impacts of those changes.
All right. Thank you, John. I am ready whenever you are.
Okay, so I'm going to hit this button here to open up VR for Mitch in the dual mode. And then I'm going to see if I can, was it getting, oh, there we go. Okay, it was loading. So if I pull up on the right side of the screen, we can see Mitch's view on the right, and we can see the IPS scene on the left. And you can also see his hands here if you look closely, sort of where he's positioned in the scene.
All right. So one of the nice things, and we'll just keep on track with the IMA side of it and some ergonomic analysis, is I'm going to come over to this stack of dunnage that we have here. This is something that we're looking at, and we maybe have to pull out some of these parts from this particular dunnage and then load them over to this seat here to my left. So what we can do is we could do several different things, one of which is just simply applying a grip point to the object and having just that done at the click of a button. From there, we could utilize a mannequin to showcase that reach, but myself being a fairly taller individual, I'm actually reaching way overhead. So John, would you actually do me the favor of lowering this dunnage down? And then I can see within my view currently about where we could move that down to. And I want the top layer kind of close to my shoulder height. So if I have my hand out here, perfect. That looks a lot better. So I can grab this part now, and I'm just going to move it into that spot in the dunnage. And now that looks a lot more appropriate for reaching and grasping and pulling out, while also considering kind of the lower end of the dunnage here. So one of the things we can do is we can apply grip points so that we can apply a mannequin posture to that afterwards. But we can also make a motion which allows us to take this part from the actual dunnage and move it over to our seat here. So I will go through and I will record a motion. Close out this window. And now when I grasp this object, I'm going to just transfer it from hand to hand, place it in the final destination, being weary of the conveyor in front of me. And if I stop recording of that motion, we could see a motion has been recorded. And then John, are you able to play that back? And I'm going to just hop over here a little bit further back so I can see that
Oh, I
motion.
clicked the wrong motion. Sorry.
Oh, no,
There
that's
we
all
go.
right. I'm going to hop over here so I can get a better view anyway. So yeah, if we play that motion, we could see that being moved from the dunnage into the position on the seat. So currently we are using the Oculus Quest headset and utilizing Steam VR to do so. And that allows us to utilize almost any headset and to connect to IPS. The nice thing that we really enjoy about the Oculus headset is that it's completely wireless and it's a much lower cost of entry when compared to some of the other headsets that are available on the market. Awesome. Thank you, John. That looks great. All right. Next, we'll hop over to another example where we can look at how we're able to manipulate cables within the VR environment as well. So,
Sorry, I'm trying to get back to a full screen here. There we go.
no problem. So you can see my hands. Are you looking at the bottom of the seat over here?
1 second. Let me get the view.
Yep.
And good to go.
Awesome. So we could see my hands here, and I'm currently looking at this cable. What we can do is we can actually grab the end effector of these cables and move it around in space. And as I pull on this cable, we can see those same tension measures that John had shown earlier being applied to this cable. So as I stretch this cable, we could see that it changes from red to blue, the opposite direction. What's nice about these cables too is as I manipulate them, if I go to wrap around, oh, the collision's been turned off on me. That's all right. There is collision detection that would typically not allow this cable to pass through this rail, but I have that turned off currently. But we could also apply a grip point to showcase maybe that there may be an issue with hand clearance when we're connecting our connector down here. We can see that my hand is running into the bottom of the seat. So maybe an approach in from here may not be the best method, or reaching around may have other concerns as well. John, can you actually do me a favor and delete this grip point that I'm looking at?
Sure.
And what I'd like you to do, John, is can you have that mannequin be attached to myself? So one of the nice features that's been recently implemented into IPS and IMA is the ability to posture a mannequin by just simply utilizing what's on you. And it will utilize the 3 locations that it has, being your headset and the 2 controllers. And now we can see I have a mannequin which will follow my motions, and I can make representative postures of this. So what I'm going to do here is I'm going to attempt to grab this connector, and by holding down a button, I'm able to run into a wall and then walk back, but I'm able to review the posture and leave a posture of a mannequin and what that would look like while we were doing an assessment here. So without the need to manually posture, it can be fairly quick to get to a posture of a mannequin, and then right after that, you can run your static evaluation. Right. And I think that concludes the portion on VR. There. So I can hop out of VR now. And that's just a little snippet of some of the capabilities of IPS within VR.
Great, thank you, Mitch. A couple of questions that have come up. You had recorded the path of the part being assembled onto the seat. Can the IPS VR session be recorded and used to analyze an assembly operation?
Yeah, absolutely. So just as we showed there, that path of that part being installed is recorded. So with John controlling my screen right now, he can make edits to that path, for example, right now. Or what we can do is we can actually attach a mannequin to that and have them follow that motion. All of that can be applied and put into what's called an operation, and that can be reviewed at a later time as well.
I should mention here as well that we have some really great just general like recording settings in IPS. So in general, we can create GIFs or videos of anything that's happening in any IPS session. So this isn't specific to VR. It could be with cable or path planner. It's built right into the software to just output a video or GIF that could then be used, in a presentation or whatever, then whatever the needs may be.
Great. And the as this is taking place in VR, can you get user feedback as you are, for instance, looking at the seat assembly about whether you were performing dangerous or injurious tasks of some sort?
Yeah, definitely. And I'm actually going to hop back to that dunnage example because I think that's very prevalent from my experience. Being able to really simulate and feel what an operator would be going through. Like when we had that dunnage in the original position, I myself, I'm just under 6 feet tall, and I was reaching completely over my head when that dunnage was in the first position there. So understanding that and being able just to feel that demand on what the posture is, even without a load, is definitely something that's very useful for anybody kind of designing any kind of product or storage or dunnage that's going to be utilized in a facility. Going over to the seat, being able to quickly apply a grip point there that could be edited and changed over. Great way to get a quick hand clearance assessment and something that you can come back and tweak later to ensure that it's actually is very accurate as opposed to just quickly in VR. It's close, but you're able to dial in the fingers a little bit more through the grip points, and you can actually get a lot more robust of a hand clearance assessment in that method.
Yes, and looking at hand clearances and so forth really has quite a bearing on the types of connectors, for instance, being selected, as well as the clips and cables.
Yep, absolutely. And just area surrounding them for installation, if any connectors kind of nested down inside of some product, just ensuring operator or assembly feasibility is a key component of what we're looking at here.
And Mitch, can multiple mannequins interact in one scene or operation?
Yeah, definitely. I don't believe in VR we're currently capable of doing that and having an interactive session, but definitely within just IPS itself, and having two operators work on a singular motion is definitely possible. So we can definitely showcase For instance, if we were going to lift up one of these seats off the conveyor, we may utilize two operators in that scenario, where we could have one operator grasping the front of the seat, a second operator grasping the second seat, the back of the seat, and showcasing the postures that both of those mannequins go through as they're lifting that off of the conveyor.
Great. Thank you, Mitch. Nope. I'll open it up for, are there any other portions that you would have liked to show? I believe we've gotten all the questions that have come from the attendees at this time.
I think that's it from us, Carl.
Yeah.
Okay. Well, then we've done very well with time. If you don't mind, I will turn the view back to myself and share my screen here.
Yeah, please do.
Actually, I'm not seeing, there we go.
Carl, just before you get going,
Yes.
I noticed that one question came in from Quality. You might also feel the mass. So we currently can't simulate a mass within virtual reality. The posture, if you do assign a mass to an object and you do attach the mannequin to yourself, the mannequin will attempt to work between your posture currently in the location of your hand and head, as well as the demands of that, the weight of that object, to push the posture prediction to be more accurate as to representing what the mass was. So directly, can I feel it when I'm in VR? No, but will the posture prediction built into IMA kind of simulate what that posture would be altered by? Yes.
Great, thank you, Mitch. Yeah, that's something in general that you know, is a corundum for VR because you know we just can't generate mass or you know to simulate weight in that manner. There is work going on in developing interfaces to VR systems that include haptic devices. Perhaps you could say a few words, Mitch, about what haptic devices refer to.
Yeah, definitely. So haptic devices typically provide feedback through vibration. So if there's ever a case of like you're colliding with something within the scene, or if a tolerance isn't met, providing a haptic feedback through a vibration in the controller will let you know to either alter your posture or alter your destination.
Great, and then another area is in haptic gloves that can simulate you grasping something, right?
Yes,
For instance,
yes.
some of the simulations that we're showing right on the screen right now. Oh, did you answer? Yeah, that I believe is work that's ongoing as well.
Okay, very good.
Right. So yes, if there are, we appreciate your time here, and looks like we're wrapping up about 10 minutes early. Again, if you do have further information, if you'd like a demonstration really tailored to your own models, the data that you're working with, or have a particular use case that we haven't addressed as part of our demonstration, we'd love to continue our conversation a bit further. As you see on the screen, there are a variety of applications really that work seamlessly within the IPS environment, from product validation to process virtualization, and the challenges are mounting as we continue our EV drive, and we're here to help you with that as well. So with that, thank you all our attendees for joining. Thanks to John and Mitch and Joanna for joining us today. And we look forward to continuing this conversation moving forward.
Yes, and just a reminder to anybody, if you're interested in looking into what IISC can offer you, please drop your email in the chat and I'll scoop it up. We are looking for more partners to expose our industrial engineering crowd to industrial engineering topics that are relevant to all sorts of different fields. So if you're from a company too, that we would be interested in trying to form some kind of collaborative experience to share knowledge, we're looking for that as well. So thank you so much.
Thank you very much. Have a great rest of your day.
Thanks, everyone.
Thank you.